So in this video, we'll talk about how to implement the string method for FhTree. So going back to one of the example we saw earlier of how we can visualize the directory tree. So here inside this directory that we ran the tree command, at this level, here are all the folders that are inside this folder, right? And then inside these folders, these are their files or other folders. And then further in, then is the file that's inside these subfolders. So this is a fairly kind of a universally acceptable way to visualize a general tree. So given that, what should the string representation of, say, this tree look like? Well, it should look something like this. So at the top, there's the tree, and the size would be very helpful that we know how many nodes we should be looking at. And the first node that's printed out should be the root node, right? Unsurprisingly. Now, the roots has three children, B, C, and D. So we should indent it kind of one level in, and then we at this level we have the node B, node C, and node D that are the direct children of node A. And now further in, then inside B or underneath B, the four children of B, E, F, G, H, right? So there'll be E, and then F, G, and H. They are all another level of indentation in under node B, and same thing for node C, that is children I, J, K. They are one level indented further inside C, and then you can apply kind of the same rule to the rest of the nodes. Another thing I want to mention is this kind of representation of a tree. It's done by what's called a depth-first traversal, because if you look at the nodes, the order of the nodes that are printed out, A, B, E, and L, A, B, E, and L. So this it prints out the nodes by going as deep as possible first before it backtracks. And there are a couple of detailed questions that we should answer before we actually embark on our implementation. So the first is, when we are at a particular node, let's say in this case node B, we can get to its sibling, or we can get to its children. The question is, which one do we visit first? Well, if you look at what's printed immediately below B, that would be node E. So that's the children first, right? So, and then if you look at E, well, immediately below E, we printed out L. So we always go to the children first before we visit the sibling, right? And you can try the rest of the row nodes and see if the same rule applies. It should. The next question is, what about the indentation? We can say the indentation kind of help us to see the structure of the tree, right? How does it change when we go to a different node? Well, if we look at this very closely, we can see how the indentation changes between siblings and between parent and child. Between siblings, let's say, for example, I, J, and K, the indentation does not change. And you can see the same thing, for example, between B, C, and D. So B, C, and D. The indentation does not change. But if when we go from a parent to a child, then the indentation increases. So if we go from B to E to L, B, and we go to E, the indentation increases. And when we go to L, the indentation increases even further. So please keep these two things in mind as we write our code. So the final question before we can write our code is, how do we actually visit every single node in the tree? Well, to go through everything, well, we usually do something like a loop, right? But it's actually slightly hard with using loop in a tree because we have to visit both the siblings as well as the children. So a much easier way and a cleaner and more readable way is to use recursion instead. And as it turns out, we're going to use recursion a lot in trees because remember what we said earlier is that a subtree at any given node is, well, just another tree. So trees really quite naturally lends itself to the use of recursion. So the question then is, well, if we want DunderString to visit every node using recursion, that means DunderString should call itself, right? Can it call itself? Well, it can, but remember, in the recursive call, we should solve a simpler version of the original problem. So that means the recursive call should take a parameter. However, the way that we usually write the DunderString method is that it doesn't take an extra parameter, right? Other than the self parameter. So DunderString, at least in its usual self, doesn't lend itself naturally to recursive calls. So what can we do? Well, we can write a recursive version of the DunderString method. We'll call it the string recurse method that does take a parameter, a node, and what this represents is the root node of a subtree that we're trying to turn into a string, right? So that we can pass it a node of a smaller and smaller subtree in the recursive calls. And now that begs the question, though, that if DunderString is to call its recursive version, then what the node that DunderString should call it with? The obvious answer is that the root node, right? Because we always start looking at all the nodes in a tree from the root. So here's the DunderString method. It has some pre and post text or string that surrounds the string that is returned by the recursive version of itself that starts its work at the root node. So let's try to write this recursive string method together. So for any recursive function or methods, we need a base case. For DunderString, it would mean the base case is a empty tree, right? So how do we know the tree is empty? Well, if the node is basically just none. So if the tree is empty, what are we going to return? Well, it's empty, though there's nothing. We're going to return an empty string. Now, we do need to return the node itself, the string representation of the node itself. So we'll make a string out of the node. We'll put a new line at the end. And now it's time to visit the siblings or the children. Remember, who do we visit first? The children. So we'll call string recurse, and we'll do node's first child. Okay, now that is going to return to a string, and we're going to append that string to the string that we already have that represents the node. Okay, so once we visit the first child, we're going to visit the sibling. All right, and again, we're going to append whatever that returns to the string that we have so far. And then once we're done, will return the string that we have kind of built. Now, with any luck, let's run it, and it actually run fine. And let's see, so this is the tree, the size is 14, A, B, E, L. We compare to what we have here, A, B, E, L, and let's say I, J, K, and the last one would be D. I, J, K, and the last one is D. So it looks like it's working. And that's what this slide is trying to explain. I believe I cover everything. And this is the output. Okay, so now the current output is totally flat. All the nodes, regardless of where they are in the tree, they have exactly the same indentation because, well, we did not implement the indentation, right? So how do we add the indentation? And if you want, you can pause the video and try to figure this out yourself first. But I'm going to go ahead and do that now. So the question we want to answer is, how do we calculate the indentation, and how does the indentation changes when we recurse to the sibling and when we recurse to the first child? So going back to this picture that we had earlier, we can see first that the deeper a node is in the tree, the further it is indented. So for example, the node L, that is the deepest in this tree, and that is the most indented in the string output, right? Along with M and N node. And that is really the direct result of that the indentation increases as we go from a parent to each child. And also remember, the indentation when we go between siblings, it does not change. So that's basically the answers that we need to implement the proper indentation. And lastly, yes, the root node, it's not indented in any way. So how do we actually do that? So I already let's see how do we modify it. So I'm going to introduce a class constant called blank that that determines how much we want to indent each time. And remember, so in the indentation is proportional to the depth, so we're going to introduce a depth parameter to the recursive version of the data string. And the way we use the depth is we are going to say blank, and we are going to multiply it by the depth, so that the larger depth the depth is, the more we indent, right? And the way that the depth changes is when it goes to the first child, the depth increases by 1, but when it goes to the sibling, the depth does not change. And the root is at depth 0. So that's that, and hopefully that will work. And there we go. Yes, the root is an indent 0, and then each of the child, the indentation increases, but B and C and D, they are at the same level or the same indentation because they're all siblings, and same for, let's say, I, J, and K. So that looks like it's working correctly. And that, I believe, is what this slide is trying to explain. So hopefully it makes sense.